want to talk about, before we move on to the next lesson, today we want to talk about how we can find the interval which the cycle is complete and when it will start over again. That's the idea. So this particular example, we'll notice when I put it into Desmos, I have the regular XY Cartesian plane, and then I switched the graph to the polar coordinates. And we see we have r is equal to 4 times cosine of theta. And you'll notice down at the bottom, I have Desmos gives us this portion here. And this portion certainly gives us the cycle in which it begins to repeat itself. And in this case, the cycle repeats itself from 0 to pi. However, notice it says less than or equal to pi. That's not true, because it would start over again, and so it would have to just be less than pi. Well, how do we do that algebraically? So when I look at this particular piece, if I were to start building a table of values, I would want to start looking at when theta is 0, can we evaluate our function r is equal to 4 times cosine of theta? So I could find r by taking 4 times cosine of 0. Well, I know that cosine of 0 using my table of values, or my unit circle, cosine of 0 is just 1. So r would equal 4. So I would have the polar coordinate for 0, which we see is right here, or here, depending upon the polar coordinates where we're at. So when will we return to this? So when I know that I go all the way around and come back, I will return back to this point, in which case I know that I'm starting to repeat myself. So our question is, when will we return to 4? So my idea then is saying, well, when is r times cosine of theta equal to 4? Well, what I could do then is replace our r value with what r is equal to here, giving me 4 times cosine of theta times cosine of theta equal to 4. Well, if I divide both sides by 4, I'll end up with cosine squared of theta equal to, well, 4 divided by 4 is 1. And so where is cosine equal to 1 or negative 1 when we take the square root of both sides? So where is cosine of theta equal to positive 1, and where is cosine of theta equal to negative 1? Well, theta would have to be equal to 1 at 0, and theta would have to be equal to negative 1 at pi. So our first cycle completes between 0 and pi. And notice here I put just less than, because if I were at pi, that is the start of the new one, right? So I would be starting a new cycle at pi. So even though Desmos does have this less than or equal to sign, that's not accurate. It's just less than. One more kind of similar to this, except we're going to use sine, how it looks with sine. And I see it's a beginning circle here. I also see that it also has the same cycle from 0 to pi when I plop that into Desmos, either using the Cartesian plane or the polar coordinates. So again, at 0, at when theta is 0, if I were to start to write a table of values in both instances, we should expect that our r would also be 0. So r is equal to, and r is equal to 3 times sine of 0. Well, sine of 0 is just 0, so 3 times 0 is, of course, 0. Shouldn't surprise us that, of course, r and theta is 0, 0, which we see graphed. So where does it come back to 0, 0? Where does it come back to 0, 0 is our question. Well, I'm starting with, of course, when will r times sine of theta come back to 0? That's the question. And again, just like the previous one, I have r. I can replace it with 3 times sine of theta times sine of theta So I just replaced r with the function itself. When will this be 0? When will we come back to 0? Well, the first thing we'll do is divide by 3 and then multiply. So I've got sine squared of theta is 0. So anything, 0 divided by anything is still 0. So when is sine, if I take the square root of both sides, we don't get a positive or a negative. I'm just looking for where is sine of theta equal to 0? Well, we just answered that, right? We just answered that. Sine of theta is equal to 0 at 0. And it's also equal to 0 at pi. Thus, we go from 0 less than or equal, that's our starting point. Our theta value continues until we reach less than pi. Because if we were at pi, I'd be starting the next cycle itself. So I don't want it to be equal to pi, just less than pi. And this leads directly into the next particular lesson. We're going to talk about some of those loop-de-loo type graphs using graphing technology to help us so we can visually see what's happening here. So it says use graphing technology to graph the polar equation. R is equal to 4 times sine of theta plus 2. So this is called a limacone. It's a limacone because it has the loop-de-loo kind of on the inside of the circle. It doesn't complete a full circle, it just kind of loops around. I see, though, it says what interval corresponds to the inner loop itself. So I see that the inner loop on the inside here, it begins at 0, and it loops around, and then it ends at 0 again. It ends at 0, 0 again. So when we're thinking about just the inner loop, it begins and ends at the origin of 0, 0. So how long does it take r to get back to 0? Right, so this is r and theta, of course. I'll substitute in r is equal to 0 for our function itself, giving us 0 is equal to 4 times sine of theta plus 2, and then start solving for sine. Negative 2 is 4 times sine of theta. Divide by 4, thus negative half is sine of theta. So where on our unit circle does sine equal negative half? There's 2 places, right? Sine is equal to negative half at 7 pi over 6 and at 11 pi over 6. So the inner loop, the part that we were just looking for, goes from 7 pi over 6 less than or equal to theta less than 11 pi over 6. That's just for the inner loop. I notice here in Desmos it gives me from 0 to 2 pi. Well, that would be the entire limacone itself. So the entire piece would repeat itself at 2 pi. We were just looking for the inner loop regardless of the outside that's happening. So be careful with what it's asking for. Here we have a 3-leaf rose, and it says use graphing technology to graph the polar equation. R is equal to cosine of 3 theta. What interval of theta value describes one small loop? One small loop. So I see here, to complete all 3 loops is from 0 to pi before I would begin repeating itself. I specifically want just one particular loop. It doesn't matter which one, just one particular loop itself. Well, we know that it's beginning and ending. Let's just grab this first one. It doesn't matter because they're all the same, because they're all starting at and coming back to the origin itself. So where r is equal to 0, our goal then would be to solve for theta to determine what options this would be for. So if I want to solve then for theta, and I have my function, we'll say 0 is equal to cosine of 3 theta. However, we haven't solved functions like this with 3 theta, so we're going to need to utilize u substitution. So let's let u equal 3 theta. Thus, 0 is cosine of u, which we can solve, of course. We're going to need 3 solutions because we have 3 loops. So I know right away that cosine is equal to 0 when u is at half, pi over 2, excuse me. U is also equal to 3 pi over 2. But again, 3 loops, 3 solutions. So I need to go just part way around my unit circle again. So also at 5 pi over 2. However, we're not solving for u, we're solving for 3 theta. So I'll replace our u's with 3 theta. And then to get theta by itself, of course, we'll divide everything by 3. Now I'll have pi over 6, pi over 2, and 5 pi over 6. Right, thinking about cosine by itself without anything, we see that it repeats itself between 0 and pi excluded, right? So we're going from 0 to pi. All of our solutions that we found are within from 0 to pi, which is awesome. That's the point, right? Because all these loops should be in there because it takes 1 rotation to go around by pi. That was just verification. I just need 1 loop, okay? So 1 loop is going to go from pi over 6 to pi over 2. Another loop is going to go from pi over 2 to 5 pi over 6. And then, of course, from 5 pi over 6, of course, it can make another rotation. So I'm just going to use the first 2. It really wouldn't matter because we're just asking for 1 loop. 1 loop goes from pi over 6 less than or equal to theta, which is less than pi over 2. That's just 1 loop. All 3 loops together would go from 0 to pi. Use graphing technology to graph. Would you call this a rose or a lemicone? So when I look at this, I have r times sine of 2 theta, and there's no picture here. It's not asking us to find any of the loops. It's just asking us to look at the graph itself. So I'm going to head over to Desmos and graph this. And I'm going to say r is equal to sine of 2. And I need to find theta, which is above the ABC button, theta. Zoom in a little and then turn it to polar coordinates. So notice this time we've got four leaves, if you will. So this would be classified as a 4-leaf rose. It doesn't have loops on the inside of the circle, which would classify it as a lemicone. So this would just be a 4-leaf rose. It's not asking us to find any of the loops, which we could, of course. This has 4 loops. Each loop is starting and stopping at the origin at 0, 0. I also notice in this particular graph, we go from 0 to 2 pi. So keep that in mind. So 0 included, 2 pi is excluded. So that would make a difference when solving if we're looking for the loops themselves. All right, something else that could be useful for us is to rewrite equations as polar equations, because sometimes it's easier to write things in and use polar equations versus the standard Cartesian equation. So how are we going to tackle this? And that will be really how we end this particular lesson, just a bunch of different examples of how we can convert back and forth. So we'll start by converting to polar equation, and then we'll start at polar equation and go to Cartesian equation. All right, so we had some definitions that we had given and used frequently in our last lesson. Have those handy if you don't already have them memorized. All right, so I'm going to first start off with x squared plus y squared is 6y. I know that x squared plus y squared is just r squared equal to 6y. I also know that I can convert y into sine because I know y is the same thing. R squared is 6 times r sine of theta. So it's already starting to look polar. by including those trig portions, if you will. Okay. But typically when I'm looking at a polar equation, all of the examples that we've given have had r equals something, right? So let's see if we can't get this to be r equals something to help us out. I see that I've got r on the left and r on the right. So I'm going to bring that 6r sign to the left-hand side. Maybe we can do some factoring. And this will be just equal to 0. I'll factor the greatest common factor, r, leaving me with r minus 6 times sine of theta equals 0. When r is equal to 0, and then I'll have r minus 6 times sine of theta equal to 0. And on the right-hand side, I'll have r is equal to 6 times sine of theta. Well, when r is equal to 0, that is just at the origin, right? That's nothing, that doesn't give us anything because it's just a point at the origin itself. So we can reject the origin. It's not anything that's useful. However, this, r is equal to 6 times sine of theta, definitely looks like a polar form equation. So now I know that I can stop. Our next example, we have just a linear equation. Right? Y is 3x plus 2, something you've probably graphed a million times at this point. You've got a y-intercept of 2. We have a slope of 3, nice straight line that's positive. What would this look like as a polar equation? And you're probably, when we get done, you're probably like, let's just stick with the Cartesian one. It makes much more sense, of course. But I don't see any x squareds and y squareds, so I can't just convert that to r squared. But I do have a y and an x. So I'm going to replace both y and x with its respective sine and cosine values. All right, so y is r times sine of theta. This is going to give me 3 times r cosine of theta plus 2. Doesn't look so bad. I'm going to put all my r's together because, again, I'm looking to solve for r. R equals what? So I'll subtract 3r from both sides. R times sine of theta minus 3 times r cosine of theta is equal to 2. Which put me in a position where I'm now able to factor the greatest common factor of r, leaving us with sine of theta minus 3 times cosine of theta equal to 2. And then, of course, if I'd like to get r by itself, so I have r is equal to something, I'll divide both sides by that sine value. So 2 over sine of theta minus 3 times cosine of theta. And of course, one way we could verify this would be to graph both y is equal to 3x plus 2 and graph the polar equation that we found and make sure that they're the same graph. They overlap one another. So when I look at r is equal to 2 over sine of theta minus 3 cosine of theta, I can kind of see where each of those values are coming from within my graph. At the same time, or within y equals 3x plus 2, at the same time, y equals 3x plus 2 is much more manageable than looking at the polar form. All right, let's do one more polar form of y is equal to the positive and negative version of 3 minus x squared. All right, we've got that weird square root. I want to try to get rid of that weird square root. So let's do that first. To do that, obviously, we take the square of both sides, giving us y squared. And now that I square it on the right-hand side, it doesn't matter if I have a positive or a negative, it'll still turn positive regardless if it started out positive or negative. So I don't even care about the positive or negative portion anymore. I just have 3 minus x squared. Well, if I bring that x squared over to the left-hand side, I'll have x squared plus y squared is 3. And we're already moving in a great direction. We know that x squared plus y squared is r squared is 3. And now I can take the square root of both sides. So the radius is square roots of 3. Not even needing to care about the positive or negative version, simply because our radius is just the square root of 3. So this is a circle with the square root of 3 as the radius. So almost a little easier in some instances to put things into polar coordinates versus Cartesian. All right. What if we want to go backwards? What if I have the polar equation and I want to know what is its Cartesian equivalent? Well, I don't like the fraction, so let's eliminate the fraction by multiplying both sides by 1 minus 2 times cosine of theta, which will be then equal to 3. I know that cosine of theta is the same as x over r. So I'm going to replace cosine of theta with x over r. So 1 minus 2 times x over r. I can now distribute r minus 2x is 3. But I still have that pesky r that's in the way, and r is not in a Cartesian equation. So somehow I have to get rid of that r, and the only way I can convert that r into an x and y is if it's squared. So perhaps the best idea might be to square both sides. But before I do that, I don't want to have to distribute anything. I'm going to bring that 2x to the other side. So I just have r is equal to 2x plus 3. So it's starting to look more Cartesian with each step. And if I square both sides, I now have r squared. And I know that I can replace r squared with x squared plus y squared. And now we've just turned everything into Cartesian. Now you could, if you wanted, expand 3 plus 2x and actually, or 2x plus 3, I should probably write it as 2x plus 3 because that's what we had it as. You could certainly expand 2x plus 3 squared if desired. You would be able to then combine it with our x squared portion. Not always needed. I've just got rid of all of my cosines and sines. I got rid of my r's, and everything is in x's and y's. And that's just kind of our main goal. Unless it specifically tells you to simplify further, you can stop at this point. Now we have r is equal to 2 times sine of theta. I know when I'm looking at this, the only thing that I can do is convert sine of theta into y over r. So I'll start there. R is 2 times y over r. The only way I'm going to be able to get rid of r is if I either have r squared or I multiply by r. So perhaps by multiplying everything by r will help me find the next step. R squared is equal to 2y. And then just like that last example, I'm going to replace r squared with x squared plus y squared is 2y. Not much else we could do to simplify at this point. So we could stop everything's in x's and y's. We no longer have r. All right, the last example. R is sine times 2 theta. Well, now we have a double angle, so we are going to need our identity sheet to help us out here so that we can rewrite it in terms of sine and cosine. We don't have within the Cartesian plane a definition for converting sine of 2 theta. We just have cosine and sine. So I'll use my double angle identity here. To rewrite it. We will rewrite this then as r is equal to 2 times sine of theta cosine of theta. Again, I know that sine of theta is x over r and cosine is y over r. So that'll eliminate the trig portion, and then we'll have to worry about the r portion. R is then 2 times x over r times y over r. This then gives us r is 2xy over r squared. Let's get rid of this fraction by multiplying both sides by r squared. I know it's going to make it look more complicated, but we'll get there. R cubed is then 2xy. We know that r squared is equal to x squared plus y squared. I also know that if I were to take the square root, that r could also be by itself the square root of x squared plus y squared. So why couldn't I replace this particular r with this and cube? This then will provide us with the square root of x squared plus y squared cubed equal to 2xy. Now you could take this a step further. This, in my opinion, is done. However, I could take this a step further if I don't like the square root and the cube piece. You could rewrite it, I'm going to say or. We could rewrite this as x squared plus y squared to the power of 3/2. So the exponent over the index, that's just there. We know that it's the square root, even though we don't write it, equal to 2xy. It doesn't really simplify it any further for us. It just eliminates the square root and writes it as an exponent instead. So either one are perfect. Notice I'm not needing to solve for y or do anything weird like that.